Hey everyone and welcome back to PrepFusion. I'm Anish and today we'll start the lecture 2B of this electrostatics chapter. So we have studied about electric field intensity and electric field due to finite line charge. So today we'll do the continuation of that. We'll study electric field due to finite charge distributions, like it will be line, surface and volume charge distributions. Okay, and also we'll obviously do few questions on that. So let's start with the line charge density. Finite line charge density, we learned about ring charge and the arc, right? Arc of a ring. Now we'll learn about the finite line charge. Here also same thing will happen. If I take a small dq charge here and small dq dash charge here, again the same thing will happen, right? Dq dash charge here, both of the magnitudes are same. So what will happen, this will again, the electric field due to this dq dash will be in this direction, electric field due to dq will be in this de direction. So obviously the y component will get cancelled, only the x component will be left, remained, right? So what will happen here, simply what I can say is de will be what? De will be simply k q. A q is not due to the small charge, right? K dq by r square. R square is this distance. This distance is r naught square plus l square. So r naught is this distance from the rod along the x direction, and l is the y direction distance. So this will be r naught square plus l square. Okay, this is a d, but actually what I am interested in is I am interested in dex. So it is basically de cos alpha. This angle is also alpha, right? This angle is alpha. This angle is alpha. So what will happen here? So we need d cos alpha, right? So what I will do is, what will be my E net? E net basically will be only in the x direction. It will be integration of de or integration of de cos alpha, right? Sorry, dex, or it is de cos alpha. So what is de? De is k dq divided by r naught square plus l square, and cos alpha is there, right? I have to integrate this. How to integrate? Now one thing you have to notice is that this time, right, this actually is not constant anymore, because here it changes because l changes, right? L changes because this changes. So it's better that I write everything in terms of theta alpha, because if I'm at this point, right, the distance changes. In the ring case, if you remember, it was always r. Okay, the distance was always same. If you remember, go back there and remember. Here distance is changing. It is a function of l. So what I'll do, what is cos alpha basically? So cos alpha I can write, I will replace sec alpha, okay? Or I can replace cos alpha. What is cos alpha? Like here, r is equals to, r is what? R is this value. R is equals to r naught sec alpha. Okay, r naught is this, or I can write this r cos alpha. R cos alpha is equals to r naught. So I will replace my, what I'll do, I will replace my r with r naught sec alpha. Okay, I will just do that just for the simplicity's sake, because r naught is constant. R naught is a constant thing, right? Distance from the rod, that is constant. So that's why I want to replace everything in terms of r naught and alpha. Okay, so I will replace. So what is what is cos alpha then? So I can write cos alpha is equals to r naught by r, but I don't want to write r, right? I don't want to get to r. I will just replace r with r naught sec alpha. Okay, because I don't want to write here r, because r is a variable. So this will come out to be k dq cos alpha is here. Okay, and okay, one more thing, what is dq basically? What is dq? Dq is simply this, right? Dq is lambda dl, right? Okay, one more thing I know is that L, right? L is equals to, I want to write everything in terms of R naught and alpha. R naught tan alpha. L by R naught will be tan alpha. So L is equals to R naught tan alpha. So what will be DL here? What will be DL? If I differentiate, DL will be basically R naught is constant. It doesn't matter. I want to differentiate with respect to alpha. So this will become differentiation of tan alpha is sec square alpha d alpha, right? So I will replace DL here. I will replace like this will be, I'll just replace this dq. dq can be written as lambda DL cos alpha, and this is R naught square. L is what L is basically this. Okay, L is R naught tan alpha. So I can write this. Yeah, L will be R naught, or this I can directly write it. R is equals to R naught sec alpha. So this in the bottom is basically R square only, right? This is R square. So this will become R naught square sec square alpha, right? Yeah, this will become R naught square sec square alpha. Now what I can write is E net, right? E net will be integration. DL is what? DL is R naught sec square alpha d alpha. So sec square alpha will get cancelled. So this will be, I will write this still, lambda times R naught sec square alpha d alpha, and this will be cos alpha divided by R naught square sec alpha. Okay, so this and this will get cancelled. So this R naught, this is constant anyway. So k lambda is also constant, right? Lambda by R naught will come outside. I will integrate from alpha equals to what? Alpha, right? Alpha can be anything. So this, let's say this angle is some, like I will integrate from, I will start from here to here. I can go from anywhere, right? I can go from anywhere. So what should be the limits basically? So this can be anything. So let's name this angle as alpha 1 and let's name this angle as alpha 2. Okay, so we'll go from alpha 1 to alpha 2. So go from alpha 1 to alpha 2. This will be alpha 1 to alpha 2. This is cos alpha d alpha. So this will come out to be k lambda by R naught sine alpha 2. From where I will start actually? I can start from anywhere. I can go from this to this as well. I can go from this to this. Both of them should be same, right? What I'm thinking is I just take care of the magnitude. So this gives me alpha. It doesn't matter. Alpha is varying from alpha 1 to alpha 2. So here, vary from alpha 1 to alpha 2. So this will be alpha 2 sine of alpha 2 minus sine of alpha 1. Okay. Now let's basically do the edge cases. Okay, let's do the edge cases. What is the edge case? If let's assume that this is a infinite rod. This is an infinite rod. Okay. If this is infinite rod, then what will my alpha 1 tend to? Can you tell me what will be my alpha 1 tending to? What will this angle tend to if this is infinite rod? What will this angle tend to? This will increase. How much maximum this can increase? This can go to maximum 90 degrees. It cannot go above that, right? This will increase this thing, right? This thing will increase. This maximum will go to 90 degrees. Okay. Here as well, this thing will increase, and this maximum will go to minus 90 degrees. Okay. So plus 90 and minus 90. This will maximum increase like that. Okay. So that is the case over here. So edge case, right? Edge case for infinite line charge. For infinite line charge, alpha 1 and alpha 2 will be 90. This will be plus 90. This will be minus 90, right? Yeah, this will be plus 90. This will be minus 90. Okay. So I will start from this alpha 1 will be plus 90. Plus I will start from this alpha 1 plus 90 to minus 90. Okay. So actually one thing I made a mistake over here. Actually this should have been alpha 1 is initially at the top. I'm going from top to bottom, right? So top should be alpha 1 and bottom should be alpha 1 to alpha 2. Alpha 1 is plus 90 and this should be minus 90. Then this will be minus 2. That is not wrong. I should go lower to higher. I will go from lower to higher. Minus 90 to plus 90. So alpha 1 will be minus 90 and alpha 2 will be plus 90. Okay. So basically what will my electric field become? It will be twice of this. Whatever is present, right? It will be 2k lambda upon r naught. If you remember, this same expression was coming in the arc length as well. There some theta expression was there, right? Some theta expression was there. This I have already been like taught here. So here the same thing I have told, that my alpha 1 and alpha 2 are basically plus 90 and minus 90. Okay. Another point, if let's say my alpha, like if I am at the edge, right? Let me copy this rod, and I am at the edge of this rod. Okay. Then it will not be symmetric anymore. Okay. It will not be symmetric. This was for the symmetric case. Okay. If I am at the edge, then what I can comment is, I can only comment about the x component. Okay, x component direction, because y component is not getting cancelled anymore, but definitely x component will be same again only. So ex will be lower to higher. So alpha 1 will be 0 and I will go to total like infinite, right? This is infinity, infinite. So here alpha 1 will be simply 0 and alpha 2 will be simply 90 degrees. So now what will be the expression? Ex will be simply k lambda upon r naught into sine of 90 minus 0. So it will be simply 1. So it will be k lambda upon r naught. Only the horizontal component, the vertical component will be there. Those I will also explain. Don't worry. Okay. So that is the case. This is for the symmetrical distribution. Okay. This I have derived for the symmetrical, because here it will be just in the middle. It will be just in the middle. So if it is symmetrical, right, it will not be alpha 1 to alpha 2. It will be actually from minus alpha to plus alpha. Okay, because it is symmetrical distribution. So in the bottom also same distance, top also same distance, so it will be symmetrical. So this, right, this will become actually 2 sine alpha. Okay, this will become 2 sine alpha. Basically all the components will get cancelled, and if alpha is 90, obviously it will be for infinite line charge. Okay, now let's solve it for the unsymmetrical case. So for the unsymmetrical case, what I will do, I will have two angles, right, alpha 1 and alpha 2. This will not be symmetrical about this axis anymore. So what I will do is that I will use the same derivation for the x coordinate, right? Here the net electric field won't be this. I will compute the electric field due to x component and electric field due to y component, and then I will just add them vectorically. So here what I will do is I will do this basically dex equals to de cos alpha, right? Dex equals to de cos alpha, and this is alpha 1 and alpha 2. So same derivation will happen. All of this will be same only. This all this thing, right, will be same. Just ex will be present, and the difference will be here, right? This is actually from minus alpha to plus alpha. Sorry, plus alpha to minus alpha. So this thing will be same only. Just the difference will be, instead of it being E net, this will be ex. Okay, so this will be from minus alpha 2 because it is in the negative direction. Okay, anti-clock, whatever direction you choose. This is, I have chosen this as negative direction. I know finally the electric field direction is in the positive x direction, right? Minus alpha 2 to plus alpha 1. Okay, so this one will actually become alpha 1 plus sine of alpha 2, because minus minus becomes plus. Okay, so this is the x component. What about the y component? What about the y component? What is the y component electric field? So y component will be simply dey will be simply de sine alpha. Everything will be same, just this will be de sine alpha, that's it. Everything else will be same. So what is de? Basically de I have already derived. De is lambda into this expression, right? Here instead of cos alpha there will be sin alpha. Everything else will be same. Everything else will be same as it is, ditto. So this will be sin alpha. Alpha will go from minus alpha 2 to plus alpha 1. This is my EY. I will integrate. Okay, so EY equals to what? EY equals to simple k lambda upon r naught cos of alpha 1 minus cos of alpha 2, because negative angle is still positive for cos. Okay, so this will be the case. Okay, sorry, here I have signed it, so extra negative sign will be present at the outside as well. So this will be flipped, basically cos of alpha 2 minus alpha 1. Okay, so these are the two components of electric field along the x direction and along the y direction. Okay, so what will be the total electric field, net electric field? Okay, the net electric field E net will be simply equals to E x ax cap plus EY ay cap, right? Horizontal and vertical component. So Ex is what? Ex is like k lambda upon r naught will come outside. Okay, this will be sine alpha 1 plus sine alpha 2, and this will be ax cap plus cos alpha 2 minus cos alpha 1 a y cap. Okay, so this is the case. So yeah, that's the thing about the electric net. So now if I do it for the symmetrical case, alpha 1 is equals to alpha 2. Okay, magnitude, basically I've already taken care of the sign. So this becomes 2 sin alpha, this becomes 0. So there is no y component. So sanity check is correct, right? Now if I am checking for one end of the line, what will be the net electric field? The net electric field, if I am checking for one end of the line, my alpha 1 will be 90. Okay, and my alpha 2 will be simply 0. If the case is like this, same case here, infinite line, right? I have computed the x component. I will check whether the x component is correct or not. Okay, so E net will be simply equals to now alpha 1 is 90 and alpha 2 is 0. So this will be k lambda by r naught, k lambda by r naught. This will be simply 1, right? Because this is 0, this is 1. Okay, 1, like this will be ax cap plus alpha 2 is 0. So this is cos 0 is 1. This will be 0. So this will be plus ay cap. Is this correct? Okay, slight change. Actually, what you do is you just determine the magnitudes and directions you put by yourself. So that will be actually the best thing. Actually, instead of writing this E net, right? I think the best expression should be you just write the magnitudes. That is the best way around. What I understood, because if you try to identify the directions, right, that will be difficult. So you give the directions by yourself. Okay, you apply the directions by yourself. This is the Ex component and this is the Ey component. That's the best way to go about it. Okay, that's the best thing, because if you try to give the directions by yourself, things will become messy. So E net here becomes what? K lambda by r naught. This will be simply ax cap, because this is in the outward and this will be in the negative direction, right? So this will be minus ay cap. Magnitude I know, as one of the angle is 0 and this is 1, so this will be this is 1 and this is 0, so this will be k lambda upon r naught, but this will be in the negative y direction, pointing towards the negative y direction. So that's the derivation basically for electric field due to a line charge. Now electric field due to infinite line charge, the infinite line charge is same, right? It will be lambda upon 2 pi epsilon naught r naught, or 2k lambda by r naught, any one you remember, that's it, right? And perpendicular and parallel, they are called as perpendicular component and parallel component. Okay, this will be actually plus minus 3 plus. Okay, so this was about the derivation. Now let's do one very simple question. So a rod of length L, it has a uniform positive charge per unit length and a total charge of Q. This has a uniform per unit charge of it has a uniform per unit charge and total charge is Q. Calculate the electric field at point P. We have to calculate the electric field at point P located along the axis of the rod at a distance A from one end of the rod as shown below. So how do we calculate the electric field due to this basically due to this rod, right? How do you calculate the electric field due to this rod? So what you can do is, in physics, what you should do, if you remember in physics, what you should do, we just computed the center of this, center of mass concept was there. We just computed the center and we assume all the charge was present over here only. And with respect to this charge, we actually what we did is replace this rod with a point charge of Q. Okay, then we measure the distance. What is the distance from this center of mass? That is what? This distance is half, right? L by 2, and this distance is A. So overall this distance will be A plus L by 2. And the electric field due to a point charge, we already know what is the electric field due to a point charge. It is E at P will be simply, this will be in the minus AX cap direction, as this is positive. So it will be K Q by A plus L by 2 whole square minus AX cap. Now this portion, right, this portion actually is wrong. Okay, this, like we use this concept in center of mass, if you remember perfectly. So this we can use only use this when A is very larger than L. Okay, when I'm very further away from this rod, right, I can assume this has a point charge only. Okay, that I can assume. But when I'm very further away, so if A is very large than L, right, then this expression EP will be basically K just hold on, yeah, r square, right, yeah, will be, because L by 2 will be very smaller than A, so I can directly write it as A square and minus AX cap direction as it is. Okay, I can do this, but now I cannot do this. Okay, now I cannot do this. So actually this is not correct. Why this is not correct? Because this, if I take a dq charge here, this will have some electric field, this dq charge will have some electric field, but the distance has changed, so I cannot simply write this as a point charge. Okay, that's why. So I have to use the basic generalized format. So I will take this rod, right, I will take this rod, and always when you don't know the electric field due to a non-uniform shape or non-standard shape, right, you just derive from basics. This is the point P. Okay, this distance is A and this overall thing is L, right? So I will take a small section that will have dq charge. Okay, and what I know lambda is equals to Q by L, because this is a uniformly positive charge, so lambda will be Q by L, it's constant. Okay, so what I can say is the electric field dE due to this point charge, right, I'm just concerned in the magnitude, will be K dq by x, right, this distance is x actually, this is varying, this x is varying, this distance is varying by x square. Okay, so my x will vary from what? X will vary from x equals to A, like this is, let's say this is the origin, x equals to, because they have mentioned this as the origin, x equals to A to x equals to A plus L. So here the same thing will happen, that E net will be integration. What is dq? Dq I can write as dq will be lambda times dl, right, or dx, because this time length is some small section x, so this will be k lambda dx divided by x square, x equals to A x equals to a plus l. So now I can do this. Now x is actually a variable. Previously x was not variable. Now x is variable. So E net will be k lambda is constant. Okay, that is simply q by l, that I already know. And this, right, this will be 1 by x from x equals to a plus l. So this will come out to be, so this, right, this type of things you need to derive at the examination hall. I cannot like derive all the formulas. It's impossible. There will be so many formulas, right? It's not possible. So E net in the direction will be, actually this will be 1 by a plus l minus 1 by a. So it will be a minus a plus l. So or what is it? X equals to a to x equals to, okay, this, right? Yeah, I can start up from here, but this will actually give the maximum electric field intensity. So as this point, right, this point is giving the maximum electric field intensity, what I will do, I will keep this as the upper limit, because at x equals to a, I am getting the maximum electric field intensity because the distance is smallest. Okay, so this dE high and this dE is lower. That's why I changed the limits. Okay, so to make the electric field positive, that's it. So this will be 1 by a minus 1 by a plus l. So it will be l by a into a plus l, right? Yeah, l by a into a plus l, and ll will get cancelled. So this will simply come out to be kq by a into a plus l. And in what direction? In the negative x direction, in negative ax direction. Okay, so this will be your answer, because they have provided in terms of a and l. So we'll write this electric field only. So this will be answer, right? This is a very, very good question. Try to revise it, because this is a very, very good question. Okay, let's move on to the next question. So these type, you can, now what is your homework? You can find out electric field at this point, you can find out electric field at this point. All these are your homework. Here only this axial component will be present here, right? Both components will be present, this like this y component and x component. Okay, so that's your homework, you can do it. Okay, so now let's solve another question. So what is another question? This question is, a finite line charge is distributed along z axis from z equals to -5 to z equals to +5. So I have a finite line charge. Let's assume this as z axis. Okay, and I have a finite line charge that is expanding from z equals to -5 to +5. with a uniform charge density of 20 nanocoulomb per meter. So lambda is 20 nanocoulomb per meter. Calculate the electric field intensity at point 2, 0, 2. Okay, so z is in this direction, so my x, right, x will be like this. It has to follow right hand rule, so x, y. So if I just curl my fingers, it will be top, so it will be like this. So I am at 2, 0, 0. So I am at somewhere around here. Okay, 2, 0, 0. So the electric field, what will happen is, this is uniformly charged, right? So electric field due to all of this dq, this is again on the axis itself. So I can directly use the formula here, or if you don't want to use the formula, you can derive as well. What I am observing is, electric field due to this component, the the z component, right? The z component will get cancelled. Only I will get electric field due to the x component, right? Electric field due to the x component. Okay, so now what was electric field due to the x component? Simply it was sine alpha 1 plus alpha 2, or 2 k lambda. If you remember, you can derive as well, or you can directly solve this. 2 k lambda 2 k lambda divided by r naught. R naught is the distance. Currently it is 2. Distance from the foot of the perpendicular. So one thing I forgot to mention, that this point, right? This point, actually I will just mention here itself. Here itself. This point is called foot of the perpendicular. Foot of the perpendicular. Why? Because this is the perpendicular and the foot is here. The ending part, the bottom part is here. That's why. So this we learn in mathematics. So now we'll do this 2k lambda by r naught into sine theta basically, or a sine alpha I can say. So what is alpha basically? So this angle, right? This is the alpha angle. So what is this alpha angle? So I can draw this in 3D, this angle. So this is 2 and this is 5, right? So base is 2, height is 5. So my tan alpha is equals to 5 by 2. So what will be my alpha basically? I will just quickly compute the alpha value. So alpha value 2.5 tan inverse 68.2. Okay, so this is 68.2. so what is sine alpha? Sine of this will be 0.982. so E along the x, right? Now this you have to identify that this is in the positive x direction. Okay, this is in the positive x direction. This will be 2 into kk is 9 into 10 raised to power 9 because nothing is mentioned, so it will be vacuum only. Okay, into lambda is 20 nano coulomb per meter divided by distance is 2, right? Distance is r naught is 2 into sine alpha is 0.93. so what will this become? Basically 2 will get cancelled. Okay, 2 will get cancelled. This will get cancelled. 9 into 20 into 0.93 into 9 into 20. So this will come out to be 167. Okay, 167.126. 167.126 in the positive ax direction, right? This will be my E net in the positive ax, because direction I will put at the end. I will just find the magnitude, direction I will put at the end. Okay, V by volt per meter. Okay, volt per meter. So this will be the answer to this particular question. Okay, so I hope you understood. Pretty simple, right? You can use the formula or you can derive it. Okay, no worries. Let's do this question. This question I will give you as homework. Okay, this question is in cylindrical coordinate, so try to do this question, and in the next lecture I will solve this question. Okay, so let's do this question. Okay, this is like a symmetrical thing. In the previous lecture I taught you the arc length as well, so pause the video and try it out now itself. Okay, try these 3 questions out now itself and I will solve this. Yeah, sorry, actually I pressed the record button and I forgot to press the record button on my iPad, so I was talking for 5-8 minutes and nothing was getting recorded. Sorry for that. So basically we'll solve this question, but before solving this question, right, I want to come back to this question. Actually I solved this question by myself, and this one I gave you homework, but I will explain this question. This is a good question. Do star mark this. Here what is happening, this is an infinite rod, so it will be the case of symmetrical electric field, right, due to symmetricity. So wherever my point is, okay, this will be, I will always assume it as the middle. So what will happen if I assume it as middle? What will happen? The parallel component, okay, of the electric field, or the horizontal component of the electric field will get cancelled due to the dq and dq charges on the diametrically opposite sides. Just the perpendicular component will be left. And what is the formula for perpendicular component? It is 2k lambda by r naught. R naught is the perpendicular distance. So this, right, I have to get the point, like this is the point about which I have to compute the electric field. So I have to mark the point of the foot of the perpendicular, so that it is a line joining the foot of the perpendicular and the point. How do I mark it? So for the foot of the perpendicular, what you have to understand is this y component, that is the, like this rod is lying in the xz component, so y is always varying. I need to fix the y will be the middle of this. So what is the y component? Y will be the same as the point that is given here. Y is 2, so this should be also 2. All the other points are already given here, 3, minus 2. So I have got the point of the midpoint of this rod, and I will connect these 2 points. This will give me the foot of the perpendicular, not perpendicular, and this point will be the foot of the perpendicular. Okay, so V vector is the line joining the foot of the perpendicular and the point. Okay, and in this direction only my perpendicular electric field will lie. Okay, so here I have got this point. So you know, right, what is the perpendicular component electric field? That is 2k lambda by r naught. We got this value electric field. Now I got this by simple position vector, simple final minus initial. Okay, I did the final minus initial, that's it, to get the position vector of this V vector. And simply r naught is the perpendicular distance, that will be the magnitude of this vector. So magnitude of this vector is under 29. So this is under 29. And then again, to write this in vector format, I need to write this V vector divided by its own magnitude, that is under 29, to write it in unit vector. So under 29 times under 29 becomes 29, and at the top I have already 360. So this question is very good. Try to repeat it again, try to go and try to solve it yourself. Main thing is this finding the point of the foot of the perpendicular, because my x and z are fixed for this rod. Y I have to fix, y is given by this point, that is the hidden information. So this point is the foot of the perpendicular. So the line joining these 2 points will be the direction of the electric field at the point P. Okay, I hope you got the question. Now let's solve this. So this I have actually solved this. So for this particular first case, pretty simple, right? What is it? It's simply a arc. It is a semicircle. So again, like the electric field due to this dq will be in this region, and electric field due to this dq will be in this region, and they will cancel. Like the horizontal component will cancel, just the vertical component will be left. So the formula we have derived previous lecture, it will be 2k lambda by r. So sine alpha by 2, alpha is 180 degrees, so it will be simply sine 2k lambda by r, and direction will be, if I assume this as xy coordinates, this will be in the minus ay cap direction, not in the plus minus ay cap direction. Okay, so I hope you got the point. Now here in the second part, right, second part, we have to use superposition, because this is, if I am observing, this is a rod with infinite length, and I am observing the electric field from a end. Okay, and same for this, and this is a circular arc. Okay, semicircular arc. So superposition principle have to be used. Okay, so this one again I will break it down. If you remember, due to this component, right, I will get two electric fields. Okay, so let's break it down. In the case A, I will get two electric fields, right, at this point O. This is the distance r. Okay, so one will be this E parallel, another one will be this E perpendicular, if you remember perfectly. Okay, so let's mark this as E dash. So E dash perpendicular I already know, right? I have already derived this formula today's lecture only. So what was the formula? I'll just copy and paste. If you remember, these were the two formulas, right? These were the two formulas. I will just copy and paste. Okay, alpha 1 is the top, alpha 2 is the bottom. So here, this is not actually ex or E, I can say, yeah, ex in ey also I can say. So in our case, it will be alpha 2 is 0, so it will be simply k lambda by r, capital R, right? Because this is 0, alpha 2 is 0 and alpha 1 is 90. Okay, what about this ey? Alpha 2 is 0, so it will be minus k, okay, yeah, it will be also 1 is 90 minus k lambda by r. Okay, but I will write the directions by myself. I will write the directions by myself only. So E dash net, I can observe that this will always give some, like this is plus electric charge, right, positive electric charge, so this will always give some downward, like this, right? So it will be downward, and here, so it will be minus ay cap, which is fine, which is with sign, that is fine. So E net will be k lambda by r ax cap minus k lambda by r ay cap. Okay, so that is the E net. Okay, now then what is the case? What about the other part, right? If this rod is in the right hand side of me, here ax cap will be minus ax cap, ay cap will be same, ax cap will be minus ay cap, right? I hope you understand the point. See, everything will be same here only. This point is O, again this distance is r. Okay, just the difference will be, this will be case B, Okay, E double dash net will be minus k lambda by r ax cap, because here electric field will come in this direction, right? If I make this positive, electric field will come in this direction. So some component, perpendicular component will be here and horizontal component will be here, right? Parallel component will be here. Again minus ay cap. So again minus k lambda by r ay cap. Okay. Now my what about the third part? This is very same, right? This is very same. Due to this circular arc, again previously it was in this direction, actually minus ay cap. Now it will be in the plus ay cap direction. Now interestingly, what will happen, you will observe, is that basically, right, everything will get cancelled and electric field will be 0. Although this is not the geometric mean, okay, but still the electric field will be 0. So due to this, right, what will happen, due to this symmetricity, my electric field will be in this direction, right? So E triple dash net will be k lambda by r plus ay cap. Now my overall E net of the whole structure, I mean whole combination, right, will be the sum of the electric fields. Okay, so how do I write it? So E net will be E dash net plus E double dash net plus E triple dash net. So it will be simply 0, because k lambda by ay and this k lambda by r ay, this will get okay, sorry, there was a 2 as well, sorry, there was 2 as well, that's why I thought this should have been 2. This and this plus this will totally get cancelled, and this will get cancelled, so hence everything gets cancelled. So it will be simply 0. Pretty straightforward, right? Now let's solve for this third case. Okay, for this case, this case is a bit different and bit interesting as well. Okay, so here again superposition principle needs to be used. This should be needs. So here, if I compute the electric field due to this, right, again I am computing, this is the infinite rod, end of another rod, right? So this formula will again be same only. This will not change. So this will be same as this case. Okay, I will just directly copy this, right? This will be same. I will just write down the axes as well. This for the case A. Axis I will just copy. What about the part B? Part B will be same as this case, right? It will be same as this case. Nothing different. Okay, no, part B will be different actually, because part B here, this is in the bottom, so things will change. Okay, I will change it. This will not be the same. So I'll just copy this. Directions will be same. So here is my point O, actually this distance is R. So electric field, this is plus plus plus, so electric field will be like this. Some will be in this direction, some will be in this direction, correct? So again the perpendicular component is this there now. Okay, perpendicular component is the EY cap direction, not the X cap direction. Okay, so it's better to write it in perpendicular and parallel. So perpendicular component is, the formula is same, that is this magnitude will be same, right? K lambda by r, like it was cos theta 1 plus cos theta 2, no sorry, sin theta sin alpha 1 plus sin alpha 2. So one will be 90, one will be 0, so it will be K lambda by r. And E parallel, again it will be cos alpha 2 minus cos alpha 1. So alpha, one of them is 0 Okay, so it will be again k lambda by r. At one end, the vertical and horizontal components are always k lambda by r. Magnitudes are k lambda by r. Directions you give at the end. Okay, directions you provide at the end. So my E net, E double dash net will be equals to, this will be minus, because this is in the minus kx direction, minus k lambda by r ax cap, but this is in the plus ay cap direction, right? Plus k lambda by r ay cap. Okay, so you get it. Now how do you solve this? Basically, how do you solve this? So now you write the electric field due to the ring charge. Ring charge will also be interesting now, because this is not a semicircle anymore, this is a quarter circle. Okay, quarter circle, this is not a semicircle, this is 90 degrees, right? This is a quarter circle. So if this is a quarter circle, how do you solve it? It will be, if I just copy this portion, it will be somewhere here, right? So actually this is my x, this is my y, this is my x, and somewhere here means this direction is what? Ax cap plus ay cap. So this direction of this v vector, right? Av vector, unit vector, will be simply ax plus ay cap divided by root 2. I hope you understand, right? It is just a bisector, simple thing, right? So these things you have to do in a short amount of time. You just cannot derive everything, it will take you huge amount of time in the examination. You should do this by intuition. Okay, so EV cap is this, and what is the magnitude of my electric field? Electric field E net triple dash magnitude, it is 2k lambda by r sine of what? Alpha by 2. Alpha is 90 this time, so it will be 45, right? So it will be root 2 k lambda by r. Okay, so now what is happening is that this k lambda by r and this k lambda by r getting cancelled, this k lambda by r and this k lambda by r will get cancelled, only this will remain. So only the field due to the quarter ring will remain, everything else will go away. Okay, so I will just write my E net will be again E dash net. I am using the superposition principle, simply E double dash net plus E triple dash net. Okay, so only everything will cancel, only this root 2 by r k lambda ax cap plus ay cap. Okay, yeah. Obviously magnitude is also there, right? Okay, this direction should also be there, this divide by root 2. Yeah, this is actually the solution of the question. This is actually the solution of the question. The magnitude will be this, okay, and the direction will be this. Okay, everything else will be simply gone. I hope you understood the point. Yeah, that will be the answer to this question. Okay, so let's move on to our next topics. A few key points that you need to understand is that whenever there is a regular shape, as I mentioned previously as well, and if I'm at the center of that regular shape, okay, the electric field will always be 0. Okay, that's basically what is mentioned. If it is a case of symmetricity, the electric field about that point will be always 0. Now, until now we have studied the electric field distribution for finite line charges and infinite line charges. Now we'll study about surface charge distribution. So if I just take like this is a sheet, just like a paper or sheet of this like small cloth. I have a sheet and this has charge, right? It is infinitely long and it has charge. So how will I solve this type of question? So again I will take some small bits. Let's take this some small bit, right? And in this particular small surface ds, I have charge dq. Okay, so the surface charge density is defined like this: sigma equals to rho s equals to dq by ds. This dq will always be with sign, remember, and ds will always be positive. Okay, because area cannot be negative, area will be positive. For now, if it is infinite, I cannot tell the charge, total charge on the sheet. If it is finite, so this will be the total charge. Okay, this will be total charge. Okay, then finite surface charge distribution. So if I have a disk, what will be the like electric field due to the disk? Okay, for now I'm just testing you the waters. So how you can write the things over here? So let's say if I want to write this in cylindrical coordinate system, how will I write it? So here rho s is sigma equals to dq by ds. So what I can write is my dl is what in cylindrical coordinates, if you remember, d rho e rho cap plus rho d phi e phi cap. I will not explain how I got rho d phi dz az cap. Now for ds, what I need to do, so identify which plane is this in. Which plane is this in? This is in which plane? In the xy plane. If it is in xy plane, so my direction will be z, and I will take the other two components. So this will be rho d rho d phi. This okay. So this is my ds and sigma, right? Like this is very useful while deriving the things. I will just explain a bit. Sigma can be written as dq by this particular thing, d rho and d phi. It will be helpful while deriving all these things, right? Just to show you how we can write it. Now if I have a hollow sphere, this is a hollow sphere, this is a hollow sphere. Like for this type of shape, right, disk and all those things, you will use cylindrical coordinate system. For sphere kind of shape, we will use spherical coordinate system. So in spherical coordinate system, again, what will be a length dl? Okay, this I should have written in vector format. Dl, actually ds direction will be what? Like it can be top and bottom as well. So it can be plus minus az cap, if you remember. Okay, dl again here will be r dr, not r dr, sorry, dr ar cap plus r d theta a theta cap plus r sin theta d phi a phi cap. Okay, so if I want to write my ds vector, right, again in what direction it is in? So this is in the, let's assume this is in the ar cap direction. Okay, ar cap. So this, if I just find the direction of the surface, right, it will be in the ar cap direction. Okay, so if it is in the ar cap direction, then I will just ignore this and I will take all the other things. Okay, and the direction will be ar cap. So it will be r square sine theta d theta d phi ar cap. Okay, and your dq by ds will become this. dq by ds will be dq by okay. So like for few uniform charge distributions, we can, like, this is not for non-uniform charge distribution, both for uniform and non-uniform. Now this, if the disk is uniform, right, I can simply divide the total charge by divided by the area of the disk. If the hollow sphere is uniform, I can simply divide the total charge by the area of the particular hollow sphere. So there can be two cases. Rho s is defined as this. Now if it is uniform, I can simply take rho s out of the integration and simply then integrate, okay, for finding the charge integration, and this will be helpful in finding the electric field basically. So that's why we're learning. This will be surface integration, right, not line integration. Okay, just hold on, I will check if everything is recording or not. Yeah, everything is recording. So this will be surface integration, and for non-uniform we have to simply integrate with the function. Okay, now we'll study electric field due to a disk of charge. Okay, due to a disk of charge. So I have a uniformly charged disk that can be considered as being made up of many concentric rings. Okay, so we know the electric field intensity due to a ring charge. A disk can be assumed as many concentric rings. Okay, many concentric rings. Okay, so that we can assume that considering ring of radius r and infinitesimal thickness dr. So its thickness, right, is very small. Ring doesn't have any thickness. Okay, so it will be dr. The surface charge density sigma is the charge per unit area on the disk. Okay, so sigma, it is uniformly distributed, so sigma will be surface charge density, which is equals to sigma is equals to what? Sigma is equals to total charge divided by pi r square. Okay, pi r square, or capital R square, I can say capital R square. Okay, the charge on the infinitesimal ring is given by charge on the very small ring. How much charge will be there? So what is the area of this? If I just break this down, right, if I just put it here and write it down, if I cut it from here, right, if I cut it from here, but like what let's say I will see this is a ring I just placed in linearly. The length of this ring will be what? The perimeter, right? Perimeter is what? 2 pi r. 2 pi r. And what is the thickness? Thickness I have told you, right? Infinitesimally small, that is dr. dr. So what I know, charge density is sigma. So sigma times small area dA will give me the charge dq, right? So what is dq here? Sigma is this. What is the small area? Small area is dr times 2 pi r, right? This will be the area of a rectangle. So that is exactly what is written over here. Sigma into 2 pi r. That area is 2 pi r into dr. That is what is written, right? So now we'll derive the expression. So how do we derive the expression? So for a ring charge, right? For a ring, we know what is the perpendicular component of the electric field, because this is again symmetric. There will not be any horizontal component of the electric field. Only perpendicular component will be present, right? Only perpendicular component will be present. Okay, so how do we solve this basically? So for a ring charge, if you remember, the net electric field was this, right? Okay, I forgot to write the charge expression over there. I think I forgot to write the charge expression. That's sad. I'll go back and write the charge expression in the ring expression, right? Where did it go? Here. Yeah, this dq. Okay, I forgot, like this will be integrated to q, right? So this will be totally charged. Forgot to write the q here. Okay, q I have wrote here, but here I forgotten to write. Fine. So here if we go, it will be q here, right? But actually in our case the charge is dq. So I can write dE in the perpendicular direction or in the x direction is equals to k. This x is the distance x, and this is the basically the main distance from the small charge dq, right? It will be r square plus x square. So it was actually the radius, right? Currently the radius is small r, so it will be x into dq small r square plus x square 3/2, and the direction is given as such. So what is dq actually? Dq is this, right? dq is, I have already written, dq is this sigma into dA, that is the sigma into 2 pi r, sigma into k into 2 pi r dr divided by r square x square 3/2. Okay, so what I can do is I can like completely get the electric field. How can I completely get the electric field? If I totally integrate this, this d perpendicular, that is my E net basically. That is the magnitude of E net. As it is a case of symmetricity, the other components will get cancelled. Diametrically opposite components will be simply cancelled. So d perpendicular will be integration with respect to what I am varying basically here. Here I am varying small disk, right? Small concentric disk. So the radius of each disk is varying. So currently the radius is r. R is variable. R will go from 0 to capital R. So r will go from 0 to capital R, and this expression will be copied. So what I can do is I can break this k down, right? What is this k? K is 4 pi upon epsilon 1 upon 4 pi epsilon, right? 4 pi epsilon. So this gets cancelled. This is just a constant thing. What other thing I can do is that I can use the method of substitution. So what I can do is r square plus x square equals to t. So dt will be 2r, because x is constant. This distance, perpendicular distance, is constant. This is not varying. R is varying, right? Small r is varying. X is constant. So this 2r dr is here, right? 2r dr is here. So I will just replace dt here. Okay, 2r dr. So what will I get basically? So this will come out to be sigma will be outside because it is uniform field density. 2 will be gone, pi will be gone. Sigma by 4 epsilon. Okay, r 2r dr will basically become dt, and this will become t raised to power 3 by 2. Epsilon is also there, t raised to power 3 by 2. So this, if I integrate with respect to dt, sigma by 4 epsilon, right? Sigma by 4 epsilon. Am I doing this correctly? Okay, here I think no, this is okay. Obviously there is a 1 by 2 will also be there. So if I integrate this, right, this will become 2 by epsilon, because this power will also be multiplied, right? So this will come out to be t raised to power minus 1 by 2 0, not 0, sorry, this limits has changed, right? Because this limits has changed now because I've changed dt. So what I can do is what is the like r is going from 0 to capital R. So if r is 0, then t is basically x square. Okay, t is basically x square. So t will be x square. So t will go from x square to what? Capital R, that is x square plus r square. Okay, so this limits will change. It will be x square plus r square. It will be x square. Okay, so this will come out to be E net. I'm just computing the magnitude. Direction I will take care later. E net will be simply this whole square, right, under root of this. So this will be 1 by x will be at that point of time. So sigma by 2 epsilon minus 1 by x, and okay, a negative sign will also be present, right? So 1 by x will actually be here. 1 by x minus, I hope you are able to do the integration. That's a simple task, right? This whole under root 1 by x square plus r square 1 by 2. So this will be the expression actually. So we don't have any other option. This is a bit tedious expression. We have to do this. Now what will be the direction? So this, if I assume some direction, right, if this is in the x direction, okay, so I'll just copy this. If I assume it the axis that this is y, this is x, so the electric field, net electric field will be simply this same expression. Okay, magnitude will be same, only this is 2 actually. A x cap, okay, it will be in the positive x cap direction. Okay, so this is the net electric field. Now let's do a edge case. If I will say, if my disk is infinite, if disk is infinite, what will happen if disk is infinite? Can you tell me what variable will change? If disk is infinite, right, it's very large disk, that means r is very high, r is very large, that means r is tending to infinity. So if r is tending to infinity, that means this expression will be 0. Okay, because r is very high, this 1 by something will be 0. So I will be only left with this expression, right? if I just see, okay, hold on, one thing I may have done here wrong. This is okay, x was also there, right? I forgot to replace the x here, sorry for it. I forgot to replace x. I didn't check the dimensional aspect of it. This should there should be x as well, right? Don't keep this. So sigma into x will be here, sorry, sigma into x will be here. I know you were screaming behind the screen that where is the x, sir, where is the x? You missed the x. Here will be x, okay, because it is a constant. It should not vary with x, that's why. So E net will be simply, it doesn't matter where I am taking the electric field, it will be constant electric field, that is sigma by 2 epsilon. This is a very important electric field expression, right? Okay, this is electric field due to infinite disk or due to infinite sheet. This is a very important expression. You should not forget this. You should remember this is a very important expression. Okay, sigma upon 2e. Sigma is the charge density, surface charge density of the disk or the infinite sheet. Infinite sheet also will give us the same expression. Okay, so yeah, that's about it on the axis of a charge, and that's how we solve this. So this is pretty simple. Just remember this expression. This expression is also very important. What is this actually? What is x square plus r square? If you remember, what is x square plus r square? X square plus r square is actually this particular length. Under root of this is particular length. Okay, let's name this as anything. You can name this. You can name this as L. Okay, so this I can reduce this to L. Okay, this length is L, or you can write this as H as well, whatever is suitable to you. So this expression is this, basically this H, and this is the perpendicular distance. That's it. That's simply it, nothing else. Okay, so I hope you understand this particular concept. Okay, so H, you can put this in your short notes. H equals to x square plus r square whole under root. Write this properly. Whole under root. Okay, so this will be basically my electric field at particular point P. Okay, so remember this expression. This expression is very important. This I have like written it here as well, same thing in good way, and infinite days also I have written. So all these things I hope you remember. You remember this unit to put in short notes. So now we'll do a few questions on this. So determine the force. We have to determine the force. So for us to determine the force, force is a two-step process in a charge, right? First electric field is generated, then I detect a force. Okay, after that, due to that electric field, a point charge q located at 0, 0, h. Okay, so let me mark the points here. X, y and z. Point is located here somewhere, 0, 0, h. Due to a surface charge density with sigma c per meter square uniformly distributed over a circular disk with radius r less than a. So in the plane z equals to 0, basically in the xy plane. So I have a disk here, okay, and its radius is simply capital R is equals to a, and I have to determine the field at this particular point P. This is simply in the axis, right? So just we derive the formula, so we can simply use it. So first of all, what distance I need? I need this perpendicular distance. I need this perpendicular distance. So what is the perpendicular distance here? It is simply h. Okay, this perpendicular distance is simply h. What about this distance from the circumference? This will be under root h square plus the radius whole square, that is a square whole under root, right? Okay, so the formula, you have to remember the formula. No, like this we have no choice. Electric field at the point P will be this sigma x is h upon 2 epsilon into 1 by x. 1 by x is 1 by h minus this distance, right? This distance is this h square plus h square plus a square whole under root. In what direction? Can you tell me in what direction? This is in the plus az cap direction, right? This will be like, this is a positive charge density. They haven't mentioned the, like, this is, we'll assume this as positive only, so this will be in the plus az cap direction. Now what about the force? What is force? Force is basically q into e, right? Simply I just have to multiply a q, and that's it. That will be my solution. So multiply a q with it, I will get back my solution. So after multiply a q, this is my solution. Okay, q is just a scalar. Okay, let's do another question. Like, these are simple questions will come. If you don't know the formula, then things will be a bit difficult. So this is a bit trickier question. So what is this question? So we have a charge with uniform surface density sigma equals to 0.5 nanocoulomb per meter square, covers the infinite plane defined by x minus x plus 3y minus 6z. Fine. Determine the electric field intensity on the side of the plane containing the origin. First of all, I don't care where I am determining the electric field intensity, because this is a infinite plane. Okay, this is the infinite plane, so I don't care about that. So infinite plane, the electric field will be constant. Okay, I don't care where I am measuring the electric field, it will always be constant, but just the direction I need to take care of. So infinite plane, I don't care where I am measuring electric field. Why? Because electric field at any point, it doesn't depend on the x, that is perpendicular distance from the plane. It is simply sigma upon 2 epsilon. Okay, simply sigma upon 2 epsilon. Now it is simply sigma upon 2 epsilon. So I will just find the direction. So let's assume like this is any plane, right? So minus x plus 3y, anywhere I have a plane, so I can have two directions, this and this. What direction I will take, that I have to identify. Okay, which point I am lying, that is also I have to identify, right? So for that I need to, for direction I care. For direction I do care. Okay, so need to identify the direction needed. How will I know direction? So I will first find out the gradient of this, that will give me the normal to this plane, and that will be the direction of the electric field, either positive or negative. I don't know, because it can be here or here. Okay, gradient will be in this direction or in this direction, anti-parallel. So I have to identify that. So first of all, I will compute the gradient of this. So phi is equals to minus x plus 3y minus 6z minus 6 equal to 0. So I will do del phi. Del phi will be minus a cap plus 3y cap minus 6 az cap, and obviously I have to divide by the magnitude of this as well to get a unit vector. So this will be what is this x what is this this is minus 1, right? So this will be 1, 9, 10, 36, so under root 46. So how do I like identify this plane, on which side this is, because they are asking the electric field on the side containing the origin. So if I just quickly draw this like vectors, right? This is x, y and z. I am observing that y is this positive end, okay, x is negative and z is also negative. Okay, sorry, x is this, right? X is here, y is positive and z is also negative. So I am somewhere around here, right? So from here I can have two directions. this and this to get to the origin. So I'm on the other side of the origin, right? I'm here on the origin. So actually this gives me the direction of this point, okay, this point, but I don't want this one because this is the minus AZ and minus AX, right? So somewhere here I will get the direction, but I want on the origin, so I will get the opposite direction because the electric field will be actually, what will be the electric field direction? The electric field direction, okay, sorry, electric field direction will be this. The direction of electric field, sigma upon 2e epsilon, will be plus minus del phi or Ag cap, right? Plus minus Ag cap. I don't know, okay, but as it is mentioning that I'm at origin, so it has to be opposite because this is telling me I'm going away from the origin. That is not possible. So obviously my Ag cap will be negative of this, opposite of this, Ax cap minus 3ay cap plus 6az cap, okay, because az cap is in positive pointing and ax cap is also positive pointing, so I will write somewhere around here, okay. So yeah, this is a good question actually. To identify the direction is a good question. So electric field sigma is 0.5 nano, whatever the sigma is, if you want to do the sigma thing, you can do that, okay, 0.5 nano coulomb, whatever it is, okay, sigma upon 2 epsilon, and the direction will be ax, take the under root as well, under root 46 minus 3ay cap plus 6az cap, okay, divided by just hold on, under root 46, okay. So this is the case here. So yeah, that's how you solve these type of questions. This is a good question. Now we'll go to a next new concept, that is electric field due to infinite sheet of charge. Just the same thing for infinite sheet and for infinite disk, the electric field is sigma upon 2e, but the direction is very important. Here the direction due to both of these sheets will be on the left hand side. Here in the middle the direction will be opposite. Due to this sheet will be on the right hand side, due to this sheet will be on the left hand side, and here due to this sheet will be on the right hand side, both, okay. So E1 and E2 will be constant, but it depends on the direction, okay. So here all of this is mentioned, and we generally, now if it is negative, right, if it is negative, the direction will just interchange, okay, directions will just interchange, and this concept we use it in capacitor. We learn this in capacitor, so do listen to my lectures right now carefully, because if one sheet is positive and one sheet is negative, basically that forms a capacitor, okay, that forms a capacitor. We'll learn this later on, don't worry. Now we'll do a few questions on this. So if I have a uniform infinite sheet with uniform surface charge density of minus 1 nano coulomb per meter square, find the electric field intensity at the point P123. So okay, this I haven't told you where the sheet actually lies, okay. This is very important, so actually I forgot to tell you. So let's assume any point, right? Let's assume the sheet is on the XY plane at Z equals to 4, okay. So okay, where did I go? So if the sheet is at Z equals to 4 plane, what will happen here is that, let me mark the coordinate axis. So my point is somewhere around here, right? X equals to, this is X, Y, Z. Point is 1, then 2, then 3. Point is here. But my plane is at Z equals to 4. Okay, so everything will be changed basically. Okay. So plane will be somewhere around here. This is the infinite plane, right? And this is positive, this is negatively charged, okay, negatively charged. So we'll take care of the direction as well. Minus, 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 okay. So electric field will be inward, Okay, I know that negative, it terminates, right? So at this point the electric field will be in the plus az cap direction, that I know. But what is the magnitude? Magnitude of electric field that I know will be sigma upon 2 epsilon. So it is minus, not minus, I will take care of the magnitude directly. Okay, I have taken care of the magnitude. Minus 9 2 into epsilon. What is epsilon? They haven't mentioned anything, so I will assume this as 8.854 into 10 raised to power minus 12. If you remember, right, this constant you have to remember no matter what. Okay, so you can measure this. Actually, you can measure this. I will still measure in front of you. One 113 volt per meter. Okay, by 2. Okay, by 2 is also there. Sorry, I forgot, by 2 is also there. 56.5. 56.5. Okay, so, and what is the direction? Direction is actually somewhere here, right? Because electric field will be terminating, so my point is here. Okay, so EP will be 56.5 a y cap volt per meter. Okay, so this will be the direction of the electric field, and this will be the solution to the question. It's very simple, but these type of question can also come. Okay, so just keep a note of this. Now this is a very, very interesting question. I will give you this as homework. What you do is you find the electric field at this point P1 and P2. Okay, point P1 and P2, you find the electric field. Okay, and this you will solve in the homework question. Okay, so let's now come to the volume charge. Okay, we'll come to the volume charge now. So if I have a cube like this, what will the volume charge? Volume charge will be this. And if you want to break this down further, right, you can break this down further. That what is my DL? Like this is in the xy coordinates only, so it will be dx ax cap plus dy az cap plus dz. Sorry, this is ay cap, right? Az cap. So my volume dv will be dx, dy and dz. Simply you can replace dv here and you can solve further. Now for spherical, what you do? For spherical, you will assume spherical symmetry. So for spherical, again I know what is my dl cap. DL cap is dr ar cap plus d r theta d theta a theta cap plus r sin theta d phi a phi cap. So my dv will be what? Dv will be just the product of all these three. Dr, just do this, r square sin theta dr d theta d phi. Okay, this will be just the product of all these two, and your rho v will be simply dq divided by r square sin r dr d theta. Okay, so this also you will just your rho v here dq by dx dy and dz. Okay, simple thing. And actually for a uniform charged sphere, okay, for a uniform sphere charged sphere, the rho v, right, will be simply q by 4 by 3 p cube. Okay, rho v. Okay, and this I will not derive right now. I will not derive. We will be derived for a uniform sphere, right? Will be derived in Gauss. Will be derived in Gauss law. I'll not derive here because the derive will go lengthy and I don't want to do that. Okay, so next like if you you can solve, if it is for any other structure, generalized structure, you can solve it with using the same methods that I told you previously as well. And one more concept is there known as electrostatic shielding. Okay, what is this concept? Electrostatic shielding is a method used to protect a region from an external electric field. By grounding a metal plate, the excess charge is conducted away to creating a region where the electric field inside is zero, effectively shielding the interior from the electric field. So actually this is just information that the electric field inside a perfect conductor is zero. Electric field inside perfect conductor will be zero. Now if the electric field inside this perfect conductor is zero, what will happen is, if I ground this, right, if I ground this, all the excess charge will go grounded and there won't be any charges here. It will be charge free and it will have zero electric field. So this particular thing will protect the protect the structure from any electric field. Okay, if I just ground this, no electric field will pass through here. Okay, no electric field will pass through here. It will not generate any electric field, because what happens if I have charge here, it generates, what happens due to induction, the negative charges are okay, this is a positive charge, right? This is a positive charge. So positive charge attract a negative charge because it is acting as a source, so it will attract the negative charges here and the positive charges will be formed here. Okay, but if I ground this particular thing, right, what will happen is that it actually gets all the excess electrons or the deficient electrons to the ground. All the electrons passes through here, so actually no electric field is generated here due to the generated positive charges. This concept we use in electrostatic, this we use in airplanes as well. Okay, but not that important. Just for theory perspective, you should know that there is a concept known as electrostatic shielding, and we use the help of electrostatic shielding with the concept of conductors. Inside a perfect conductor, the electric field will be zero always. We take this concept. Okay, this you should know. And that's it for this lecture. Electric field has been finished. So we'll learn about electric flux in the next lecture and Gauss's law. Thank you for watching, and I will see you in the next lecture.